This conference will now be recorded.
Okay, hello everyone. It is 1 o'clock on the East Coast, and we are going to go ahead and get started with our presentation today. My name is Jessica Enix, and I'm with the AHCIL staff, and I would like to welcome you to today's webinar. Before we begin the presentation, I'd like to review a few points of protocol so that you'll get the most out of your webinar experience. Remember, you are listening to the webinar via a conference service. If you are disconnected, repeat the steps that were given to you by the registration email. In order to reduce background noise, please be aware that all participant lines will be muted throughout the presentation. If you have any questions during the presentation, please type them in the chat box. A chat icon is located at the top right-hand side of your screen. The presenter will address questions as they become available or at the conclusion of the presentation. Please note that today's program is being recorded. Now it is my pleasure to introduce our two presenters, Mr. Bruce Quimby and Mr. Ed Connor. Bruce Quimby is a senior application scientist in the mass spectrometry division of Agilent Technologies, located in Wilmington, Delaware. He received a Ph.D. in analytical chemistry from the University of Massachusetts and a bachelor's degree in chemistry from Mansfield State College. He has been at Agilent Technologies since 1979, working the first 10 years in research and development. He has authored or co-authored 18 journal articles and 16 patents in the field of gas chromatography and mass spectrometry. He is working in GCMS applications in multiple areas. Ed Connor, who will present second, joined Peak Scientific in 2013, initially working as a technical specialist before joining the product management team in 2017 to manage Peak's precision gas generators for GC applications. Prior to joining Peak Scientific, Ed completed his Ph.D. at ETH Zurich, conducting analysis of plant volatiles by GCMS, and then worked for 5 years as a lab manager at the University of Zurich in a research group specializing in GC and GCMS analysis. In his spare time, Ed enjoys traveling, music, and hiking. Ladies and gentlemen, we will get started with Mr. Bruce Quimby, so please welcome Bruce Quimby.
Thank you, Jessica. So I'll get right into it. The title of my presentation is rather dull. My supervisor sent it in. Anyway, what I'd like to do is cover a few interesting things that we think you will find useful. These are, I'll jump right into it. We're introducing a new single quad GCMSD system, the 5977C, and you'll see that it's very much similar to the 5977B, but we have a choice of sources and multiple gas chromatographs to which it attaches. And I will go to the triple quadrupoles, where there has been a number of interesting developments. This is the 7000E triple quad, and we have, of course, the inert plus EI source, or what we call the extractor, the CI, of course. But we have a new source called hydroinert, which is available. It's an extractor source designed for use with hydrogen carrier gas. And this is available for both the 7000 series triple quads and for the 5977 extractor source GCs. I'm sorry, mass specs. And this is the 7010 with the high efficiency source and also CI available. So now let's look at in the case of both of these series of instruments, there's been improvements in the software that allow you to reduce your downtime. It has intelligent technology that monitors the system of the health, and you can reduce GCMS maintenance by, there's a counter for how long the filaments have been on and things like that. For labs that are looking to talk about their sustainability. We have a number of things that will help you there. A recent one is the My Green Lab ACT label that talks, it's a label on our instruments that gives the viewer a idea of how green our instruments are. So what I first wanted to do was, as an applications chemist, talk about things that are interesting to analysts. And the the first one for our triple quad is we have a new acquisition mode, the simultaneous dynamic MRM scan. And of course, dynamic MRM gives you excellent sensitivity and specificity for analyte detection and identification. We've known that for a long time. But because dynamic MRM is fairly efficient in its use of acquisition time, it allowed us to put in simultaneous DMRM scan so that you can also get scan information while you're collecting your chromatogram. Now, the first question I gave to my colleague who was running experiments on this is, well, if you're not spending your time looking at, not spending all of your time looking at your DMRMs, how much do you pay in terms of signal to noise? And she said it's very small. It's maybe a factor of 2 at most. And of course, what the scan would allow you to do is confirm the identities of a, let's say, a surprising find if it's at a high enough level with a library search, or if you have a non-target and you want to go back and look and see if there's something there. One useful thing is to check for matrix overloading and interferences. So if your extracted matrix has a huge amount of material, let's say in the center section, you might want to know that at least the first few times you run it. And of course, you can do retrospective analysis. You can go back and look if there was something there that you weren't looking for before. And so here, for example, is the acquired spectrum of delta methrin out at the end of the chromatogram here. The other new acquisition mode for GC triple quad, and this sort of came to us from our LC folks, is triggered MRM. And this is where we go along and we're looking at, let's say, the target and qualifier MRMs for a pesticide like chlorpyrifos methyl. But if we think it's actually there, in other words, if this one shows up and we start to get a response on the quantifier ion, then what we can do is have a threshold set. And when the quantifier ion goes over that threshold, it will acquire several other MRMs. And that would give you much greater confidence if it's a really important compound that doesn't show up often, but when it does, you'd like to have more evidence that it's actually there. We've been requested to offer a manufacturer's recommended tune for our Agilent GC triple quadrupole MS instruments. And that's because if you want to, for example, use MRMs to do some of the EPA methods, well, there's no DFTPP tune for the triple quad mass specs. And so we now offer that communication of what the recommended tune parameters are. And of course, we've been recommending tunes for, 50 years now. And it uses reported values from the check tune and auto tune report, and it focuses on sensitivity, mass resolution, and mass accuracy. And it applies to the following GC triple quad instruments: the 7000 C, D, and E, and the 7010 A, B, and the new one C. And if you're in need or think you might find this useful, on our new instruments, the 7000E and 7010C, this manufacturer's recommended tune and letter will ship in the instrument software itself. And for earlier instruments like the 7000C and 7010A, you can find out more by contacting your salesperson. So now I'd like to get into a longer discussion of hydrogen carrier gas for EIGCMS. So as you've probably seen, there's yet another shortage of helium now, where not only has the price gone up, but in some cases, people aren't getting helium shipped to them, which can be a real big problem for GCMS. And so people are considering alternatives to helium. And really, there's only one logical carrier gas, and that's hydrogen. So the first thing I want to bring up is that people often have hydrogen safety concerns. Here's a quote from Air Products, where hydrogen safety concerns are not a cause for alarm. They simply are different than those we're accustomed to. One of the things to point out is hydrogen is lighter than air and diffuses very rapidly. So it doesn't do things like methane, where it will pool in an area and then cause a big problem. And it can be handled safely when simple measures are observed. How do I know that? I've been handling hydrogen for about 45 years. And many of our labs already use it with their flame ionization detectors and things like that. So in any case, I'll be offering some places where you can get more information on hydrogen safety, but our instruments have been designed to handle hydrogen for at least 40 years. And then later in this presentation, you'll hear about different sources of hydrogen, including the hydrogen gas generator. All right, so this is kind of an older slide where it says, don't switch from helium to hydrogen unless it's necessary. In other words, we wouldn't want you to do just recreational hydrogen GC mass spec, but the reason why we say that is, if you're going to switch to hydrogen, and it may be necessary, you want to make sure that you allow time for method development to go in and successfully change over. So the first thing is, hydrogen is a reactive gas, and I would almost modify that as somewhat reactive, but you have to watch out for reactions, and I'll say more about that in a minute. So chemical reactions may happen in the inlet, and we've seen some happen there. In the column, very rarely, and in the source of the mass spec that can change your results. And that's one of the most important ones, is the source itself from our findings. Oh, sorry. If you're looking at switching over a quantitative method, you want to check every analyte in every matrix that you're running in every method and validate it using hydrogen to make sure that you don't have chemical reaction problems. Looking for for untargeted unknowns can be problematic due to the possibility of reactivity, and we can minimize that if you follow a couple of our suggestions that'll be made later on. The same way with library search, match quality will be impacted for some analytes, and I'll show you some results from that. Tuning results will be different than with helium. Turns out they're not a whole lot different. Some tunes, notably BFB and DFTPP, may not pass. And of course, depending on the helium situation, you can first try helium conservation measures instead of switching to hydrogen. Of course, if you've been shut off by your helium supplier, that's not going to help a lot. All right, so in converting from helium to hydrogen carrier gas, it's important to recognize the differences, and you do need to allow time for adapting the method. Areas that will need attention are your choice of hydrogen supply, and you will hear more about that in a few minutes. GCMS hardware changes, source or lens, choosing new chromatographic conditions, and this one will happen to almost everybody because of the lower viscosity of hydrogen. You'll almost certainly end up with a smaller bore column, but you'll also end up with higher resolution that may help you speed things up. There's a potential reduction in signal to noise ratio due to a higher noise, and I would say that's you can count on losing a factor of about 2 to 5, just a broad generalization. Changes in spectrum abundance ratios for some compounds and activity and reactivity with some analytes. So I would strongly recommend, if you're considering switching from helium to hydrogen, to obtain this document from our website. It's a detailed guide to converting from helium to hydrogen, covering all the topics that I just mentioned. It's about 34 pages long, and it covers safety and picking column diameters and things like that. So I would strongly recommend you look at this if you're going to consider switching. So in that guide, for example, if I had to make a list of what items would I have available if I were going to switch over a method, the first one would be we need to use a different diameter drawout lens, or these are drawout lenses for the older instruments like the Inconel or the stainless steel source. These are extractor lenses for the newer extractor sources. And I would use a 9mm lens if that was the only one I was going to get. There, you can also try the 6mm lens. Many environmental labs already have these for 8270, even with helium. And probably the least usable one is the 3mm. There's, I'm sure, a few situations where this might work, but there's too much reactivity right around here for many of the compounds. Okay, so this is our new development for people that want to use hydrogen carrier gas with our GC mass specs, and it's called HydroInert, and it's a extractor source that fits in. It's got the same shape and mounting hardware and everything, and so it's a direct replacement for your standard inert extractor source. And now I'll go over a few um, examples of the benefits that you would get. So the first thing is it greatly reduces in-source hydrogenation and other reactions with the analytes. Another reaction might be dechlorination. So a number of the strange things that we've seen using hydrogen carrier, and it isn't that you get bad results with everything all the time. It's that there are some compounds that misbehave because of the presence of hydrogen. And this greatly reduces that. It significantly reduces spectral fidelity problems. It improves the peak shape for high boilers like the later eluting PAHs in 8270. And it gives improved calibration linearity versus the non-hydroinert sources. So here's an example, and nitrobenzene is probably the poster child for hydrogenation. If we look at nitrobenzene here, if we have nitrobenzene in the presence of hydrogen, heat, and a catalyst, and the catalyst is usually a transition metal, we can readily make nitrobenzene into aniline. So here's our NIST spectrum for nitrobenzene. We should have, 77 as the base peak, 123, and 93. The worst case, if you use the 3 mm drawout lens with hydrogen carrier in the extractor, notice we get the 93 is dominant and much bigger than the 123 or the 77. In other words, you're basically looking at the spectrum of aniline, even though it comes out at the retention time of nitrobenzene. So if you do the extracted ion chromatograms for 77 and 123 down here, look at the 93 and look at the big tail on it. Well, that tail is from a surface reaction where we're converting this as the nitrobenzene goes through the source. So here we have the inert extractor shown here with a 9 mm lens. And the 9 mm lens significantly improves this 93 problem. But you see that the 93 and the 65, the 93 is too big and it's still tailing substantially. And so we get a poor match for nitrobenzene, which remember is supposed to look like this. The nitrobenzene spectrum is in fact here, much of it is aniline. With the new hydroinert source with a 9 mm lens, here we have 77 where it's supposed to be, 123 where it's supposed to be, 93 and 65. Now, if you look closely, there is a little bit of tailing on the 93. So in other words, the hydroinert doesn't absolutely completely get rid of every bit of it, but it's a very substantial improvement. And now our library mat score is 94. The other substantial improvement when we have hydrogen present and we have these late eluting PAHs like benzo B and benzo K fluoranthene, benzo GHI parylene, and indeno 1,2,3-CD pyrene. We get the best performance before hydroinert anyway with the 9 mm inert extractor lens when we're using a hydrogen carrier. But we still get this tailing on the PAHs. And under the same exact chromatographic conditions, if we use the hydroinert source, you can see that we get dramatically reduced tailing on those lady looters, which is helpful if you want to uh, get higher resolution on these. So you can see that right here. Okay. So this is from an earlier set of experiments where we wanted to look at the calibration linearity of 8270 over zero point 0.1 to 100 ppm. And this is in sim with an MSD. That is a single quad. So the reference is down here, and this is our best effort before hydroinert, where it's the inert extractor source with a 9mm lens. And so this is, we had 68 compounds that we calibrated, and 42 and 43 of them passed the average response factor RSD less than 20. 6 compounds required linear fit, and 20 and 25 required a quadratic fit, and 25 and 26 required manual revision. Up here are the hydroinert results, where we substantially improved basically all of these aspects. And we're not surprised. So for example, the nitrophenols and things like that were substantially happier. And here's our average response factor RSD. And as you can see, in general, it's better. Now, there's later app notes on our website that have just come out that are much more detailed, covering hydroinert and 8270. And one of the problems with that funny business going on with the nitrobenzene, where we were converting it and things turning into aniline, is the calibration curve was not good. And now it is with hydroinert. So here's our 10 levels, and here's the library mat score. In this case was 94. This just shows an improvement in the library mat score comparison. Now this was done by Angela Smith, where here's the library mat scores with the 3mm extractor and helium, comparing it to the NIST library. And as you would expect, they're pretty good matches. Now, not all of them are super, like 4-nitrophenol was a little less than 90. This is the library mat scores with that same 3mm extractor, but now with hydrogen. And she did this to highlight the ones that might be most upset by the presence of hydrogen, because the 3mm lens accentuates the problems. And as we can look down here, some of them paid a fairly substantial price. And then over here, we see the 9mm hydroinert results with hydrogen carrier. And they are, in general, very good and compare well with the helium results. So we're quite pleased with that. Okay, I wanted to quickly mention the volatile organic compounds. And in this case, this is some work that I did with a headspace unit and used hydroinert. So this is a 80 compound volatiles mixed. And in this case, I'm using pulse split with a 20 meter 0.18 1 micron column. You will probably, if you switch to hydrogen, end up with a 20 meter 0.18 column. That's a real good fit for the viscosity of hydrogen. And about 0.95 mils per minute. And I used sodium sulfate to salt out the volatiles, and a calibration from 0.25 up to 25 for the scan mode, and 0.05 up to 25 for sim mode. So the first thing I wanted to look at was, well, okay, how do the library mat scores look for all of these volatiles? And quite frankly, they look great. The average is 94. Here's nitrobenzene. Yeah, it's 94. These other ones that were lower than that, some of them were real bad actors, like this chloromethyl cyanide. There was just so little of it that actually came out of solution that we got a bad mat score. Acetone was a problem, and I forget why. I think it was, oh yes, too low responding. And in general, the library mat scores are just great. So we're real pleased with that. Here's iodomethane. I got very good linearity from 0.05 up to 25 ppb. This is scan mode, and here's sim mode, both looking at the 0.05 ppb standard. And the MDLs, as measured by taking the standard deviation of the response from 8 runs of the lowest calibration standards and taking 2.998 times that standard deviation. The MDLs for the method came out quite good, down in the part per trillion range. We got very good linearity with that, by the way. So in summary, for my section, there's new models of the MSD 5977C. The most exciting thing about them, at least to me, is the hydro-inert extractor. For the GC triple quad, there are multiple very interesting new things. The simultaneous DMRM and the triggered MRM, the manufacturer's recommended tune, and hydro-inert. And then if you are considering switching over to hydrogen, I would suggest that you investigate the hydro-inert source, because it clearly does greatly reduce in-source hydrogenation of analytes. It dramatically reduces spectral fidelity problems. It gives you a really nice peak shape for high boilers like PAHs, and it gives substantially improved calibration linearity versus hydro-inert. And so with that, Jessica, I would like to turn it over to my colleague, Ed O'Connor, so that he can talk about where to get hydrogen from.
Wonderful. Thank you, Bruce, for your presentation. I have turned the presentation over to Ed. So ladies and gentlemen, just bear with us a minute while we get this turned over.
Oh, and there's some references at the end where you can get more information.
Sorry, I just realised I need to unmute myself. So hopefully you can see the presentation.
Yes, we can.
Yep, perfect. All right. So thanks, Bruce. That was was very interesting, and hopefully there'll be some good questions on that at the end of the session. So yeah, I'm now going to just give you an overview of the main considerations for hydrogen safety, and with a focus on gas generators. So first of all, just to give you an overview of the benefits that gas generators provide compared to gas cylinders or other bulk supplies. First of all, generators provide a round-the-clock supply of gas on demand, so they allow you to eliminate cylinders from the laboratory and mean that you don't have to keep monitoring levels of gas in cylinders, worry about whether they're going to run out over the weekend or of an evening, for example. Another benefit of generators is the consistent gas quality that they provide. So the gas is produced using a repeatable process. So in the case of hydrogen, we have a thing called a proton exchange membrane cell, or a PEM cell, where we separate hydrogen from deionized water. So we electrolyze the deionized water, produce hydrogen and oxygen, and retain the hydrogen and supply that to your GC. And so this means that you are free of impurities other than oxygen and moisture from a gas generator, which is different to gas cylinders, which can contain things like hydrocarbons. Then when we look at the economic benefits, obviously there is an initial cost to buying a gas generator, but once you've invested in the gas generator, the ongoing costs are relatively low. In the case of our hydrogen trace generators, it's simply a replacement of a filter one time per year, so and that's pretty inexpensive. So you can see long-term benefits to your operational costs as you use generators over the years. Safety is probably one of the primary reasons that people will invest in hydrogen gas generators in particular, and I've got more information specifically focusing on the safety benefits of generators in the following slides. And then another aspect, and of course there's an increasing focus on carbon footprint and reducing our environmental impact, and generators certainly contribute to this. Just if you think about how cylinders are typically supplied via a truck, obviously the trucks will go from the depot to your laboratory multiple times per year, and so there are potentially significant emissions from those deliveries. With a gas generator, you can have the gas generator delivered to your lab and it will remain on site for its entire operational lifetime. So in terms of the highlights of why a gas generator is safe if we compare it to gas cylinders, first of all, a generator will have a very low stored volume. So our hydrogen trace systems contain less than 300 cc's of gas at any one time. So if we compare this to a large gas cylinder, this can contain over 9,000 litres of compressed gas when it's full. So there's quite a difference there. In terms of the internal pressure, our systems deliver up to 100 psi, so that's 6.9 bar pressure. Again, if we contrast this with a cylinder, we're typically looking at 200 bar plus. So you can already see that despite the fact that a generator can supply an entire laboratory, it's operating at much lower pressure and with a lower stored volume. We also have a number of safety features built into our gas generators so that we're monitoring for leaks and also monitoring pressure constantly to prevent any leaks into the laboratory atmosphere. And I've got a calculation to show you afterwards, but again, the time it would take to actually release a sufficient volume of gas to reach the lower explosion level of hydrogen it would take days, basically, with supply from a gas generator, compared to a cylinder which could provide that volume of gas within minutes. So in terms of the safeguards that are built into the Peak Scientific generators, when you switch the system on, we have a full pressure decay test to make sure that there are no internal leaks. And if a leak was discovered within the system, then we would produce no more gas and alert the user so that they can check if there are any leaks, for example, in the connections between the generator and the GC. We also have forced air ventilation so that we're preventing any buildup of hydrogen and oxygen within the generator if leaks were to occur internally. And we are constantly monitoring the pressure both within the system and between the system and the GC, again, just to prevent any risk of leaks occurring. Now, there's not only, of course, a potential risk of leaks, but if there was some other failure within the system, it's possible that the pressure within the generator could become too high. So again, we have fail-safes within place to prevent internal pressure rising too much. And we would shut down supply of electricity to the cell in this case. And so if there is an alarm, we will stop supply of electricity to the cell to prevent any more hydrogen being produced. We will depressurize the system. And again, when we talk about depressurizing, it's a small volume of gas, just 300 cc's or less. And again, there'll be an alarm that will let you know that there's a problem. We also have put together a list of consecutive failures that would need to occur for a critical buildup of hydrogen within the system. So I won't go through these in too much detail, but basically we would need 8 consecutive failures of multiple components within the generator to have a risk of an explosion, if you will. So basically, it's almost impossible for this sequence of events to occur. And in addition to this whole sequence of failures, we would also need an ignition source close to the generator. And as Bruce mentioned in his presentation, hydrogen is extremely dilute or diffuse, so it will not collect and pool within the laboratory. So again, it's extremely difficult to achieve the lower explosion level, or LEL, of 4.1% within a typically used laboratory space. So we do have a number of customers who have switched to generators, of course, from cylinders. For those who've switched from helium, there are obviously the benefits of being able to get away from cylinders altogether and to use only generated gas. The other key benefit is the reduction in manual handling and the risks associated with handling heavy cylinders. So here I have the worked example just to illustrate again how difficult it would be to achieve the lower explosion level of 4.1% in a laboratory using a generator. So if we take a laboratory measuring 5 meters by 4 meters with a 2.5 meter height, we would have a total volume of around 50,000 litres. And so to reach the 4.1% LEL, we would need just over 2,000 litres of hydrogen. So if we contrast a large hydrogen cylinder with a generator, again, the hydrogen cylinder would contain around 9,000 litres of gas when it is full. So releasing just a quarter of the contents quickly would mean that we could actually reach the lower explosion level within a short space of time. So it certainly is conceivable that this could happen with a significant leak of gas into the lab. If we contrast this with a hydrogen generator producing up to half a litre per minute, it would take almost 3 days to produce that same volume of gas. And so this is really why a lot of Peak's customers are investing in gas generators, because it basically means that you can have that ready supply of hydrogen in the laboratory without that risk of any mistakes leading to a sudden release of gas into the lab environment and the potential risks following that. So yeah, basically here's another customer quote, basically where they've moved to generators to eliminate the possible risks of cylinders being deployed in the laboratory. Depending on where you're located as well, it's worth pointing out that we are seeing customers who are being increasingly restricted in where they can deploy hydrogen cylinders. So we're aware that a number of laboratories now require that hydrogen cylinders are located outside the laboratory, whereas generators can be operated within the laboratory, and we would actually encourage you to use them close to GC instrumentation to reduce the number of connections in the pipework between the generator and your GC. And so by having it close to the GC, it means you can keep an eye on the generator, make sure the deionized water's topped up, but also it just reduces any risk of introduction of any impurities via leaks. Okay, so just on to the last couple of slides now. So here I've just got a list of the certification that we have on our generators, and it's really important actually, if you are considering investing in a gas generator, that you look at the certification that the generator has. One of the key pieces of certification that we have is the CSA certification, and part of the testing that we had to undergo to obtain the CSA certification was the dilution test, which is from the IEC, a UL standard for laboratory use of hydrogen. And what we had to show there was that if all of the internal volume of gas from the generator was to leak into the generator without the fans operating, that we would not reach the lower explosion level, so that the generator really presents no fire or explosion risk. So yeah, it's just an important thing to look out for if you are shopping around for gas generators. Another key bit of certification that we have is the ISTA testing, which means that we have done drop testing and so on the generator, so that it will arrive at your laboratory in one piece. Again, it's important that your generator arrives in good condition, is well packaged, and you can start it without any issues. Okay, so finally, I've just wanted to highlight a couple of documents that we have on laboratory safety, which are available from the Peak website. So we do have a number of articles on hydrogen safety. So if you are concerned or looking for more information, you can certainly find lots of information on the website. We have user stories where, if you're interested in the experience of other laboratories having switched from helium to hydrogen, we have a number of examples there. We also have an overview of changing carrier gas from helium to hydrogen, which focuses on particularly on the installation and the steps you should consider in terms of the gas supply to your GC, as well as some of the key points for the GC. But as Bruce mentioned, the article from Agilent is certainly very comprehensive. So definitely pay attention to that as well. And yeah, there's plenty of other information that we have available. And if there's something else that you're looking for that you can't find, then feel free to get in contact with us via the website. Okay, so that's everything from me. I'll hand back to Jessica, and I think we'll move to the Q&A.
Okay, wonderful. Anyone, if you have questions, please go ahead and type them in the chat box. You will see a chat icon located at the top right-hand side of your screen. So we will give you a few minutes to go ahead and get those questions in. It is not looking like we have any questions at this time. So, gentlemen, if you have anything else you'd like to add.
I have a question for Bruce.
Okay.
Bruce, I know that looking over the last few years where there have been various application notes using hydrogen carrier gas, many of them have used SIM detection, presumably by way of getting around some of the background that can be seen when using full scan with hydrogen carrier gas. I just wondered what you've seen with the hydro inert in terms of SIM versus scan.
Whenever you use hydrogen carrier gas, you always get a bit of background spectrum, and I'm not exactly sure where it comes from, but there's quite a few ions in the background spectrum, so that will reduce your scan sensitivity for some of the compounds, and it depends on which ions you're using. But that's fairly common, and with the hydro inert, it's reduced, but it's not eliminated.
Okay,
I am not any other questions. Ed, did you have anything else?
No, not at the moment. Yeah, I can't see anything that's been typed in.
Okay, well, with that, I will thank you both for the presentation today, and we will go ahead and wrap up the webinar. Again, this program will be recorded or has been recorded and will be on the ACIL website, so feel free to view it later. Gentlemen, thank you, and thank you for everyone attending today.
And goodbye.
Okay, thank you. Bye-bye.
Bye.